All right, folks, welcome to day 10 of Organometallics. Quick administrative announcements. You'll note that we're coming up on the midterm, so that'll be next week, Thursday. Hopefully you have had a chance to get some practice through the homework set. And if you're looking for additional practice problems, just want to draw everyone's attention to from my lab website, the resources page. You can access all of the old years of this class, the midterms, finals, problem sets. And so that's a great resource. Nothing is meant to be secretive, so it's all open and out there. There's not going to be repeat questions, but you can get a good idea for the flavor of questions that we have asked in years past. And so that's how I would direct you. In addition, of course, to reviewing the notes and all the typical test prep strategies you use, I would direct you to those resources. Is there anything else we want to add on the administrative side?
Problem set is due today after class. If you haven't submitted it, please send us an email.
Great. Any questions on administrative issues for the upcoming midterm? All right, if not, we'll jump into it. So we're in day 10, but we have some catch-up work to do from day 9, which is fine. We'll get through this batch of notes as quickly as we can without rushing. Some of this will be review anyway, so that itself to going through quickly. And it's really about establishing a foundation, core concepts that are useful in catalysis, and then core concepts, some of which we've touched on in various bits and pieces throughout the lecture in terms of thinking about ligands, ancillary ligands, and their role in catalytic cycles. So first, we'll start out just by defining some terminology and situating that terminology in the context of potential energy surfaces. This should come as no surprise at this point in your chemical education. I'm sure you have seen this defined before. A catalyst is a substance that will increase the rate of a chemical reaction without itself being consumed. This goes back to Oswald's definition from the 19th century. In the context of homogeneous catalysis, what we're typically expecting to happen is the catalyst is undergoing a series of elementary steps in a particular sequence that then regenerate the catalyst, which is used sub-stoichiometrically. So in principle, just based on this Oswald definition, a catalyst could be used, it could be a reagent or could be something that is used sub-stoichiometrically. And in the literature, this can be, I think, misconveyed. So I just add a brief comment here. There's catalysts, something that can be a catalyst even if it's used stoichiometrically, and then we just call that a stoichiometric catalyst. And then what we typically think of as catalysts, the things we add in small quantities, 1 mole%, that perform multiple turnovers, those are sub-stoichiometric catalysts. That's a very clear definition. In the literature, you see people fumbling over this and saying this reaction is metal enabled, but not metal catalyzed, and it can be very confusing. But in principle, a catalyst can also be stoichiometric. There's nothing that violates any definitions. It's just in that case, it's a stoichiometric catalyst. So in terms of the potential energy surface, we can take a quick look. And again, the refresher here is that the key point is that if we consider a model reaction, A plus B goes to C plus D, there are kinetic and thermodynamic descriptors associated with this bimolecular reaction. And the presence or absence of a catalyst doesn't change the thermodynamic descriptors. So that is the delta G, delta H, delta S, and the corresponding equilibrium constant associated with that transformation. What it does change is the kinetic The presence or absence of catalyst changes the kinetic descriptors, which are delta H double dagger, delta S double dagger, delta G double dagger. So again, kinetics, thermodynamics, common theme from the class. And so in the context of most of the examples we will cover in this course are thermal reactions, meaning that there's no, the reactions are not out of equilibrium. So what are out of equilibrium reactions? Those are photochemical reactions, those are electrochemical reactions. We're typically talking about thermal reactions, which are in equilibrium reactions. And so a consideration that's worth thinking through at the outset, let's say you dream up a reaction and you want it to proceed thermally in the presence of a magic metal catalyst. It's worthwhile considering, is the reaction actually thermodynamically downhill? So let's consider a case study of a representative hydroamination of the type shown here. If you do the math and you just sum up bonds made, bonds broken, you can convince yourself that this reaction is close to thermal neutral, which means that the reaction, depending on factors like stoichiometry of starting materials, concentration, pressure, the equilibrium can lie either to the right or to the left because it is close to a thermally neutral reaction. So the presence of magic ligands that promote this reaction will not improve the product yield if this is the product you want, if it is thermodynamically not preferred. And so if we consider this reaction, and let's imagine the kinetics that it has a low barrier, and you just wanted to push the reaction to the right, what would you do? Al, this is most relevant to you. So how would you push this reaction to the right?
In terms of equilibrium, one possibility is using making one of the reagents excess like the amine.
Beautiful. So add more olefin, add more amine. This is an A plus B goes to C reaction. And so by Le Chatelier's principle, if we increase the concentration of one of the starting materials, we can drive it towards the right side of the equilibrium. So again, thermodynamics, the key thing that you need to, and you can just do this back of the envelope, you just do an inventory of the bonds that you make and the bonds that you break. So what do we do here? We are making an N-carbon sigma bond and a carbon hydrogen sigma bond. And then on the left side of the equation, what have we lost? We've lost a CC pi bond and we've lost one NH bond. And so that effectively defines the thermodynamics of the reaction. Okay, back to kinetics. So if we're talking about how to accelerate a reaction, something that we will often encounter, we want to lower the energy barrier for the turnover limiting step, and we'll define what that means. And I think the Hartwig textbook is really rigorous in this part of the textbook in terms of defining things really clearly and defining core concepts of catalysis, and then also generalized catalytic cycles and complicating factors therein. So in a catalytic reaction, how can you make a reaction go faster over its turnover limiting step? There's two approaches essentially. There's one is the transition state stabilization approach, where we're affecting this key barrier and this level we're lowering, and the other is ground state destabilization, where we're affecting the barrier here by increasing the energy. So this is TS stabilizing, ground state destabilizing. So let's consider now a generic catalytic cycle. And, in general terms, this can be a little bit confusing, but I think if you actually just think this through in the context of specifics, it becomes a little bit clearer. So you've all done a catalytic reaction at this point in your career, I'm sure of it. And what do you do in that reaction? You have some pre-catalyst, let's say you're doing a Suzuki cross coupling, that pre-catalyst could be palladium acetate. That itself is not necessarily the active catalyst. It might need to undergo a series of elementary steps or redox adjustments to get on cycle. So in the case of palladium acetate for a cross coupling, palladium-2 is not the active oxidation state for a cross coupling, so it needs to get down to palladium-0 through in situ reduction. Then you generate your active catalyst. And from that point, it can do a couple of things. What you hope to do is it coordinates substrate molecule, abbreviated here as S, and forms some sigma complex, or potentially undergoes an elementary step like oxidative addition in this analogy of, in this case of a cross coupling, or it can be coordinated by some inhibitory species in solution. So example, if you have excess phosphine ligand, the phosphine can start mopping up the coordination sites and pull the active form of the catalyst off cycle. Coordinate your substrate, and then you hope that it will undergo your productive elementary step. But again, here from this species shown here, there are other things that can happen. For example, this could dimerize and form an off-cycle species. So you hope it undergoes your productive elementary step to get to now an intermediate, abbreviated here as I. Here, two things can go wrong. In this case of a cross coupling, after you make your aryl palladium through oxidative addition, the palladium carbon bond can be protonated off and give you an inactive form of the catalyst and a undesired form of the product, i.e. a byproduct. And then you hope it undergoes some additional elementary steps. In the case of a cross coupling here, that would mean another coupling partner comes on, S prime, to generate a new intermediate, and then further elementary steps to eventually form product. So I think what's nice about the way the Hartwig textbook lays this out is that it doesn't assume every catalytic cycle is going to be the idealized catalytic cycle where it turns over infinitely. It specifically maps out these deactivation pathways. And why this is important is because this is more of a reflection of reality. How many times have you run a catalytic cycle and asked yourself, in an idealized catalytic cycle, I would only need, in theory, 0.1 or even less mole percent catalyst, but what I'm using is 20 mole percent. A lot of nickel catalyzed cross couplings, they're 20 mole percent catalyst, 30% and 50% yield. So that's telling you right there, it's the catalyst only turning over about 2.5 times. What else is happening? And it's all of these hidden steps that we don't see in the idealized catalytic cycle. And some people actually don't even like drawing the off-cycle processes that are certainly going on because it makes their nice catalytic cycle look less aesthetically appealing. So don't do that. Okay, let's consider problem today number 1 from the day 9 worksheet. So if you don't have it, I can pull it up quickly. And we've been talking about cross coupling, so no surprise here that this example, this problem of the day is meant to allow you to think about a cross coupling and think about it in the context of what we just talked about, the idealized cycle, and as well as the things that can go wrong. So take a minute to think about that if you haven't already, and we can start getting some ideas on the board. For example, the proposed catalytic cycle, we can map that out, and that might help everybody think about deactivation pathways. All right, Sebastian, give me a plausible catalytic cycle here to get us started.
Okay, let's see. So
So your starting material is nickel what?
nickel 2.
Okay, so let's first talk about, is this going to be on cycle or is this before the cycle?
That's one problem. If we continue with analogies with palladium stuff, that's probably not going to be on cycle. You'll have to turn it into nickel zero.
How are you gonna do that?
And maybe DMA.
DMA, okay, what do you like about DMA?
Well, it has an amine on it, and maybe that will do kind of a similar mechanism like that we see with like amines and activating palladium 2 to palladium 0.
Okay, so, yeah, I mean, DMA sometimes might have, so you could imagine, these are basic reaction conditions, so I think what you're saying is, let's imagine we hydrolyze some of the DMA, or sometimes DMA just comes with diethylamine in it, and then you have an amine activation mechanism. What do you mean by amine-based activation mechanism?
I think you will have the amine displace chlorides on your catalyst. And then from there, you can, I think, use one of the CH bonds from the methyl to like insert into your nickel, and then you can do a reductive elimination. That would get you back to nickel 0.
Okay, so you, stop me if I have anything wrong here. So you said you coordinate the amine, you do beta hydride elimination, you generate an imine, hydride, and then the hydride upon treatment with base. You lose HX. Generate your zero valent metal center. Okay? Yeah.
Can sync your the coordinate with nickel and then displace the chloride.
How would it coordinate? What's that elementary step?
Association.
Well, so we've got, you know, what if I drew this in generic terms here? You have a RM and you have.
Oh,
a
transmetallation.
tribe CL. Yeah, okay. Good, transmetallation. I'm just drawing this to, with the cis-trans isomerization to simplify things, and then what do you like happening next?
That's the that will try. Yeah.
Zero, and then you have two tricyclohexylphosphate ligands. Okay, great. So we covered two common mechanisms activating a +2 oxidation state metal in situ. One is the amine-mediated method, and then there is the so-called double transmetallation reductive elimination mechanism. And then the third that we won't cover here because it's probably not operative is a mechanism where the phosphine is an in situ reductant. Okay, so we've got nickel 0 now with some phosphine around. It looks like we might be on cycle, so give me one more step here. And I've got you. What do you think's gonna happen next? Okay, into the OPIV. What are you gonna oxidatively add into? Got it. Okay, beautiful. So this is a trick that nickel can do. Palladium doesn't do this as well, that nickel can oxidatively add into carbon oxygen bonds, even when they're things like carbonates or phthalates. Palladium typically only does that well when they're triflates. Transmetallation. So why it's worthwhile thinking about things like catalyst activation is you realize quickly if you're consuming, let's say you're just trying to wonder why you're using 10 mole% catalyst and your maximum yield is only 80%, right there you've got an answer, is that you consuming two equivalents relative to the metal of one of your coupling partners. So you've got an excess. And then what do you like happening here? Anybody get anything different or have questions about that? Okay, there's our idealized catalytic cycle, and then things might not go according to plan. So what could potentially not go according to plan here? Right.
For example, the organozinc can saturate the nickel, and upon exhaustive reductive elimination, it generates nickel zero particles. And they go off cycle the solution, and you have heterogeneous nickel zero.
Okay.
Very inactive.
So let me think about that. So from, if I understand, maybe I can just generalize this, which is to say that if you, from this zero valent nickel, which is true of a lot of zero valent metals, you always run the risk of not being able to sufficiently stabilize them to get to nano, and then they will form nanoparticles or clusters. In your case, I think you're saying this could be potentially promoted by the zinc. So,
Yeah, I mean, for your chemical reaction, right? If you remove also the phosphines, without phosphine around, I think nickel zero will be average.
sure, okay. Other ideas? Yeah, Oliver.
This is more of a question. Why do you form the nickel black? Why is it? It's just not stable. It's the complex form, so just
Yeah, I think that's
something.
a way to think about it is that you know, anytime you're like zero valent metals have a general proclivity to, you know, to find each other. And so if you're ever in a situation where you're unable, like in catalysis, I'll give a philosophical answer. In catalysis, it's all about navigating a bumpy ski slope downhill. And if you think about an analogy to skiing, are there ever any ski resorts that are fun where you go way downhill and then you just get to a valley and it's like you have to manually hike up another hill to continue down the run? Typically not. And so it's all about having these kind of shallow potential energy wells. And so what that means is that when you're asking a homogeneous catalyst to navigate this potential energy surface, it needs to like be able to find and react with substrate. So it needs to have a sufficient amount of potential energy, but that potential energy surface also, that potential energy that gives it the opportunity to react with itself and form aggregates and get off cycle. If you can put metals in coordination environments where they will never form the metal black with pincer complexes or tetradentate ligand, but they also don't do any chemistry. So that's the high level philosophical challenge here, is that when you start having higher and higher degrees of polydentate coordination, it will definitely stabilize the metal against deactivation, but it won't do anything. It won't have the kinetic reactivity it needs for things that we care about, like cross couplings. What else could be going on here? We talked about nanoparticle formation. Al's got something.
If you there is under air of there, or if there's an oxidant, can you oxidize the phosphine? And that might be inactive.
Okay. So potentially we could come back here if we have O2. What else? Mike, do you have something?
Yeah, the oxidative addition complex, you could probably form a dime, like a bridged pivalate dimer.
Oh, okay. That's a cool thought. So,
I was thinking before you transmetallate,
oh,
when
okay.
you have piv.
Right, that's what you said, but I missed it. So this would be, these are all great answers, so. Let's see if I can capture this. What you have, and so this could be bridged with one, it could be bridged with two pivotates. I'm just gonna draw it in the most simplified form. This is the general idea. Yeah. Alex, let's get maybe one more thought.
Inheritable arrow species can be proto-demetylated by just trace adventitious water or something.
Love it, yeah, so this, at this stage, it could find a proton, or at this stage, it can find a proton. And notice I'm drawing these without the equilibrium arrow, because this could be the end of the road here. So this eventually gets you to nickel 2. This, or in this case, or the same here. One more possible process that we haven't drawn, I don't know if anybody's thinking about it, is we talk about nickel's ability to engage in single electron transfer. But we avoid that in this case, and the idealized catalytic cycle were 0, 2, which is seemingly a good thing. But you also have this omnipresent possibility of your catalytic cycle has nickel 0 and nickel 2. Your pre-catalyst is nickel 2. And what can happen if you have a nickel plus 2 plus a nickel 0? A new elementary step that we haven't covered so far, proportionation, which is where two atoms of a different redox state come together to form two atoms of the same oxidation state, and it's microscopic reverse disproportionation. Beautiful. Okay, how about C? And I think we actually have some thoughts on this too, about zinc chloride decrease in catalytic efficiency. I mean, you see this all the time, people adding random additives, seemingly random additives, and they boost yield. This is a case where actually additive decreases yield. And how could it be doing that? Yeah, I think you touched on this already, so it's great to circle back to you.
I think it's because of Le Chatelier type effect on the transmetallation state, because byproduct of the transmetallation is zinc chloride, mixed salt of pivalate and zinc chloride. So if you have more zinc salts, you are suppressing formation of that salt. So decreasing the rate of transmetallation.
So you're saying that actually when you transmetallate here, we kind of drew this in simplified form, and what you really have is some like this plus what comes out of the cycle is zinc chloride pivalate, i.e. zinc 2 salt. And this can form some kind of interaction with,
If we zoom, it's just zinc 2 source, so you have more zinc salts around.
Yeah. I think you're touching on a key important point here, which is it goes back to an interaction that we covered briefly, which is that low valent metals, remember these are very electron rich, in the presence of Lewis acids, what can they form? So they can form this Z-type interaction. And in this case, they were actually able to identify a zinc nickel, and I won't draw the structure here. I'll include the reference for this from Ruben Martin's group. But I won't draw it out because I'll make that would take the rest of the lecture. But it makes a well-defined zinc nickel cluster that's inactive. And the mechanistic details of how that assembles is not really critical for this discussion. But the key point, hopefully, that comes out of this is that for a relatively simple looking reaction, there is a lot of complexity behind the scenes of things that hopefully are working on your behalf, but also forces that can be working against you. Questions on that? All right, let's keep trekking forward then. Some of these terms I've thrown out already. I'll just rigorously define them. Turnover number, that's a very easy and intuitive one. This is just moles of product versus moles of your substoichiometric catalyst. So easy example to think about, a reaction that runs with 1 mole% palladium catalyst and gives a quantitative yield. That's 100 turnovers. And then the turnover frequency is the number of turnovers completed for a given unit of time. And so these two descriptors, the first one is a readout of how stable your catalyst is over an extended period over its lifetime. The second is a readout of how reactive, i.e. how fast kinetically active your catalyst is over a defined period of time. And both of these can be important in different contexts. Typically, an idealized catalyst does both well. It's highly kinetically reactive and has high turnover number, but which is more important depends on your given application. In the Hartwig textbook, they take care to define and discuss in detail what I'll present next, which is thinking about the underlying kinetics for an idealized catalytic cycle. And the key point here is that in a catalytic cycle, after the system reaches steady state, the rates of each individual step are identical. And the step that controls the rate, I think this makes sense intuitively, but sometimes like the formalism is more confusing than the intuition. The step that controls how fast we go around the circle is called the turnover limiting step, i.e. the step that has the smallest pseudo first order rate constant. If we were to study each elementary step in isolation, this would be the step that is the slowest. And the catalyst resting state refers to then the species that is the highest concentration before the turnover limiting step, and that can include an off-cycle species. So sometimes it's stable for the catalyst to rest as its dimer, for example, and then get to a reactive intermediate and then react further. That's what we define as the catalyst resting state. When things work on your side, when luck's on your side, you can directly monitor a reaction running in situ and read out the catalyst resting state, for example, from NMR or React IR. Sometimes it's more complicated than that. And then as a consequence of this point that is starred, the overall kinetics of a given reaction cannot obviously exceed the rate of the slowest step times the concentrations of the catalyst and reagents at the T0 time point. So I think none of this is new, but hopefully just seeing it for a second time and seeing it defined rigorously is helpful. Bless you. As organic chemistry practitioners, we use homogeneous catalytic reactions. We use heterogeneous catalytic reactions on a day-to-day, week-to-week basis. The heterogeneous reactions you're probably most familiar with are things like hydrogenation over palladium on carbon. There are pros and cons to each approach, and how much you weigh the pros and cons also depends on the setting that you're operating in. So for example, for us in academia, we might care less about having hyper high performing catalysts because we don't need to deal with the waste remediation and the catalyst contamination and downstream products. But in an industrial setting, they will care much more about that. So the pros for homogeneous catalysis are selectivity, tunability of the ligands that are used, and the ability to control selectivity outcomes based on the ligand structure, and having well understood mechanisms. And we talked about the cons for separation, and this can be really tricky in the context of pharma, and we'll hear lectures that will touch on this, guest lectures that will touch on this point later, because oftentimes the products that you are generating on large commercial scale are these nitrogen-containing heterocycles that themselves are strong ligands for the metal, and separating metal-containing byproducts, metal salts, from the organic products you care about can be a major issue with homogeneous catalysis when applied on scale. And you don't have to take my word for it. You can take the words of the experts we'll hear from. And then the advantage of heterogeneous catalysis, typically these are very highly reactive, low cost, recyclable. So think here, some of the reactions that are performed on planet Earth on the largest scale, those that are society underpinning reactions, are heterogeneous reactions. Haber-Bosch process, for example, petrochemical cracking reactions. But in the context of small molecule synthesis, these are typically insufficient in terms of their selectivity, and sometimes have slow rates at the operating temperatures that we like using as academic chemists. Okay, this brings us to problem of the day, number 2 from the last time's worksheet. I don't have the reaction scheme written out, so I'll just do a quick swap over in case you don't have that worksheet handy. We've talked about, we're going to talk about hydrogenation. This is a different type of hydrogenation than is most common. Most commonly, we're talking about pi bond hydrogenation. This is a sigma bond hydrogenation where we take a diphenyl ether, and in the presence of nickel, high temperature H2, we replace a carbon oxygen sigma bond with a new carbon H and OH, two sigma bonds. So this reaction, some of the signaling elements that might make you suspect, this could be, I'm not 100% sure this is homogeneous, would be extreme operating conditions. So you've got H2, you've got high temperature, long reaction time. And if you look and you say, what are the strongly coordinating ligands? This is directly related to Oliver's question. If you said, what's going to prevent the catalyst, the nickel, from forming nickel black, from finding each nickel atom from finding its friends and aggregating with them and precipitating out of solution? You'd say, I'm not really convinced anything is a strong ligand. We've got TMEDA, that's not a super strongly coordinating ligand for a late transition metal like nickel. Nothing else really stands out. So those are signaling elements that think, okay, we should at least ask and answer this question about whether this is homogeneous or heterogeneous. So what the question tasks you with, imagine you're the student or the postdoc who has this result, and you're going to write the paper, and clearly you need to be able to say something about the mechanism and disambiguate between homogeneous and heterogeneous catalysis. So what are some of the experiments you might do? So there's a lot of reasonable answers here. So I'll just give you a couple seconds here to think about a few, and then I'll invite a few people to volunteer. Julian, what do you like for one?
Not sure.
All right, anyone want to jump in? Nima, what do you think?
I don't have any certain answer. Maybe by just looking at the solution or filtering it out, we can realize, or maybe by just measuring the absorption and have the standard sample of the starting material and product, because the absorption should be different in the heterogeneous and homogeneous conditions, right? Because of the fraction. So maybe that helps.
Okay, so you had a couple different answers. So one is filtration. So how would we do this? We would set up the reaction, and then at some point you would either at the reaction temperature or maybe let it cool, then you filter. You take the filtrate, you charge again with substrate, and you see if it's active or inactive. Okay, and then the other you said was some type of spectroscopic technique. And there are several that could work here. So nanoparticles, depending on their size, can interact with light, and so you could so here the key is you need some so for example UV, but you need some reference material. Thanks.
In this case, reference should be fine because we have phenol, benzene, and the starting material is basic. So we can make a standard sample and just measure.
But I guess right, there could be an active homogeneous form of a nickel catalyst that's colored, and there could be a nanoparticulate form of the nickel catalyst that's colored. So that's what I mean where you.
Yeah.
Reference these three. Oliver, do you have one?
Yeah, like heterogeneous reactions tend to be very sensitive to agitation. You use like magnetic stir bars, you get coatings and stuff, which grinds up the particles, and so it allows them to keep reacting. Whereas if you use like overhead agitation, it just dies,
Okay.
stops. I don't know if that would be relevant in this case though.
Yeah, this is a good, let's assume that all the other components are homogeneous. And then in an idealized homogeneous reaction, if you change stir rate, it does not change reaction rate because those reactions are not mass transfer limited. In an idealized heterogeneous reaction, mass transfer effects can still affect the rate. So I think so there are some other points that would need to be true, but if they are true, then you could, that would be a reasonable thing to consider. More volunteers. Let's take Ning-Shi first.
I think a common method for, maybe not now, but a common method for excluding a heterogeneous mechanism is to add mercury. And then if it's heterogeneous, it would probably be deactivated.
Say that one more time. I just
Liquid mercury.
add liquid mercury. So that's known as the mercury drop test. The idea is that nanoparticles will aggregate, amalgamate with mercury, and that would deactivate a heterogeneous reaction. Pierre, you have one?
You see how reaction rate depends as a function of amount of catalyst added, like the order of catalyst with respect to reaction.
Yeah, so I think in general, kinetic profiling, quote me on this for Donna so I can get in her good graces. Kinetic profiling is a great idea. And so one of the hallmark features of a heterogeneous reaction is that you will often have this sigmoidal shape. Where in this period, effectively all that's happening is the active heterogeneous nanoparticulate catalyst is being generated. And then once it's generated, it's off to the race. So you can even do things like combine this with filtration. So after you've generated the active form, then you should have no induction period, for example. What else? Any other thoughts? Riku, did you have one?
Is that a question? How would
Yeah.
you know if it's partially homogeneous? Like, if you're heating it to like 120 degrees in xylene, like how would, for example, a filtration, like practically, you're gonna cool it, right, when you do the filtration. Like,
Well, you can filter hot. There's nothing that breaks any laws of physics to do a filtration hot.
I was wondering if like, how would you know if it's like, for example, like partially? Is it difficult?
Yeah, that's true. I mean, in practice, it's this broader question. So I think the question we're laser focused on here is the catalyst homogeneous or heterogeneous. There are a lot of homogeneous catalytic reactions that exhibit characteristics of heterogeneous reactions because they have an insoluble base or something like that. So I think if you put yourself in that frame, you'd say like, okay, actually this scenario I'm kind of familiar with because I know that in a Suzuki coupling, the inorganic base is often insoluble. And that's an example of kind of a hybrid homogeneous, heterogeneous overall reaction, catalyst homogeneous, but other components are heterogeneous. So a couple others here just to get down. One is you can do, it's not that common, but it's a nice design. You can basically do the inverse of a mercury drop test. And that is to use a strong chelating ligand. So in this case, it's a dibenzocyclooctadiene. This is rigid, and so it coordinates through both of its olefins, bidentate coordination to metal. This will deactivate a homogeneous catalyst, but not deactivate a heterogeneous catalyst. And then another experiment that, just being in this department, I can't help but highlight, is developed by our emeritus colleague, Julius Riebeck. It's called the three-phase test. So in this case, what you do is you immobilize one of your substrates. For example, you put it on a polymer bead. And then you can imagine, I think this makes sense intuitively, reactions where you have a homogeneous component reacting with a homogeneous component are generally fast. Reactions where you have a homogeneous component with reacting on a surface, i.e. with a heterogeneous component, are fast. Reactions where you have two solid phase immobilized components reacting are extremely slow. And so if you immobilize one of your reaction components and the reaction slows down dramatically, then that's a signaling element that you're in the heterogeneous regime. In this particular case, the Hartwig group found that this phenol hydrogenation was heterogeneous. And the reason why they're interested in this is this linkage is relevant to lignin depolymerization. Questions on this? Okay, let's keep marching through. Now we'll shift our focus to a subset of homogeneous catalysis, which is asymmetric catalysis, where we're focused on preferentially forming an enantiomer of the desired product through desymmetrization of some kind of prochiral starting material. Terms here, you may have encountered this already in a phys-org class, reface, psi-face. So reface, psi-face, I think just one of the things I sometimes hear, which is incorrect, is that re goes to R and psi goes to S. That's wrong. So it depends on a number of different factors, but reface, psi-face, you basically take your flat starting material, you assign priorities based on the standard CIP rules, and then depending on whether they're clockwise or counterclockwise, you get re or psi. And then likewise, related but not equivalent are pro R versus pro S. And here I've just drawn this hypothetical CH iodination reaction to illustrate that point. The descriptors are figures of merit, so to speak, from a catalytic enantioselective reaction, are of course yield, but then enantioselectivity, which is most commonly still in the year, and it's not really obvious why we even do this anymore, still in the year 2025, the most common way that EE is reported, or the enantioselectivity is reported, is via EE. And that's really a vestige of earlier times. In the olden days, the best readout for the level of enantioenrichment of a organic compound was optical rotation. It's so-called optical purity. And as it turns out, optical purity is directly related to enantiomer excess. So this became a very convenient way for people to report enantioselectivity because, bless you, they could just read out the optical rotation, optical purity, and then report effectively directly on EE. But the issue with EE as a reporter is that it doesn't directly linearly correlate with what you care about, which is the delta delta G double dagger, whereas an enantiomeric ratio, ER, does. And so I think the younger generation, or even some of the more senior colleagues who are more grounded in phys-org, have been trying to push the community to adopting reporting as standard practice ER, because then it's just easier to plug that into your linear free energy relationships or understand your computational results that are typically reporting on delta delta G double dagger. For kinetic resolutions, EE is not the most illustrative or meaningful descriptor, because you can always run the reactions to super high conversion and then have only 10 molecules left in solution of perfectly optically enriched material. So for a kinetic resolution, remember what you're trying to do is you have typically a racemic mixture and you're trying to react off one hand of your molecule of interest. And an idealized kinetic resolution, you run it to exactly 50% conversion, meaning every single molecule of one hand is converted to whatever you're converting it to. If it's an alcohol, maybe you're doing an acylation, and then left unperturbed is the other hand. But in practice, the selectivity is not perfect, so you need to run it sometimes beyond 50% conversion, where you've actually started consuming some molecules in the left hand, and that's why selectivity factor accounts in not only the EE, but also the level of conversion that you ran the reaction to. Some general rules of thumb, just to ballpark ourselves, or benchmark ourselves, are this is a really helpful one. In terms, if you're, in the academic literature, everybody cares about, and it's totally arbitrary, but this is what people have chosen to care about, achieving 90% EE. And so that corresponds to about 2 kcals per mole until at room temperature in terms of the delta delta G double dagger. And why this is kind of arbitrary is, what is the practical difference between 88% EE and 90% EE? It's like a 0.1 kcals per mole. Does that really matter? Is that the difference between work being high impact or low impact? I'll leave that to you to think about. So we'll consider now some types of catalytic asymmetric reactions. And here we're organizing by what the potential energy surface looks like. And we're going from more simple to more complicated. The simplest case is where the enantio selectivity, the left hand, right hand, is determined in a single step. Maybe I'll back up and just say, what do we mean when we say enantio determining step? What we mean there is the enantio selection takes place at the first irreversible step that involves the chiral, effectively, that involves the chiral ligand that proceeds through a diastereomeric transition state. And so this is important to think through rigorously, because the enantio determining step is not necessarily where your bond in the step where your bond in question is formed. You can have, for example, a situation where the step you care about, let's say it's a hydrogenation, maybe that olefin is getting hydrogenated reversibly, and actually what's determining enantioselectivity is dissociation of the product. I think that's a rare, that would be a very specialized situation, but I just say that to illustrate this point, that your enantio determining step is not necessarily directly involving the bonds that you care to be making. Okay, so now let's consider these examples, these categories organized by potential energy surface, shape of potential energy surface. So the first is single and antidetermining step. So think here, things like some types of oxidations of sulfides or epoxidations like Jacobson epoxidation, where your bimolecular collision, you have your catalyst with chiral ligand, and you have a bimolecular collision event with your starting material of interest, and that forms your new enantioenriched product. And then it's very simple. It's just, let's say you have an olefin, and here's your catalyst. Does it hit this way or this way? And the only thing that you care about is the delta delta G double dagger between those two collisions. But that is simple. And it turns out most reactions that we care about don't fall into that category. Most have multiple steps that are reversible prior to an antio determination. So I think the type of reaction, and this ties directly into what's supposed to be the focus of today's lecture of hydrogenation. So I think this goes hand in hand. This is most commonly illustrated with discussion of hydrogenation. So we're in this general category of having a more complex potential energy surface with multiple steps. And then we're going to consider some sub-scenarios within this category. So let's first consider the simplest case within this more complicated situation, and that is where the interconversion of a diastereomeric intermediate, in this case, because we're considering hydrogenation, a metal olefin complex is slow relative to the rates of conversion to product. So in this case, it's pretty simple. The substrate can, so if we start in the purple regime, we've got substrate, we've got catalyst, and it's going to bind. It can bind in two faces, red or blue, and then once it's bound, it's locked in. You've determined antioselectivity. So if you consider yourself imagine you're the olefin, you can bind on your stomach or on your back. And then once you've made that choice, everything else happens. Then you're getting a back massage, or you're getting a pectoral massage or something if they're a bodybuilder. I don't know. I don't know if people do that. But then once you've bound, then the downstream steps are fast. That's the key point. And then you have, within this more complicated potential energy surface category, you have the most complicated scenario, which is what we generally refer to as Curtin-Hammett control. And that is where interconversion among your intermediates is faster than the reactions, the elementary steps that form product. And there are several different flavors of this. I think the two that illustrate the point most clearly I've tried to draw out here. And so the first is where the more stable intermediate reacts faster. That is, we have this differentiation, which face the olefin it's binding. And then, though that's reversible, that's coming on and off, the more stable binding one is also the faster reacting. And then the opposite can also be true, where the catalyst is trying to find what face to bind, and it finds the more stable face, and so it's perseverating on this longer, but this is the only one that reacts. It's shorter lived, but reacting faster. And often people, because more stable reacts faster, more stable, okay, I have this right. More stable reacts slower. And so a lot of times people will, in the literature, they'll only refer to this scenario as Curtin-Hammett, even though the whole regime is technically Curtin-Hammett. Okay, questions on that? Went through that quickly. Yeah, Amy.
Sorry, will you explain the difference between those two? It's more stable, reacts faster, or more stable, reacts slower. Is that?
The left is the more stable one, the longer lived intermediate is reacting faster.
Okay.
On the right is the more stable, the longer lived one is reacting the productive step slower.
Okay.
So in the classic Landis, so one of Donna's favorite papers of all time is the Landis-Halpern hydrogenation paper. Actually, I mean, this is one of the most important Fizzor papers of all time. It's this regime. So when you observe where the catalyst is resting, you see that it is resting at an intermediate that would lead to the minor product. So how could that be the case? It could only be the case if that intermediate is more stable but slower reacting. So it goes and it sits there and it doesn't proceed to product. It just sits there until it can get to the other intermediate that then reacts through a shallower, traverses a shallower barrier. Questions? Okay, we'll talk about ligands, and we'll do this quick since we introduced some of these concepts before. So what are the ligands that we care about in terms of ligands that can affect the reactions that we're working on? So the most commonly, these are phosphines, or in the past 20 years, N-heterocyclic carbenes for specific reactions that are generally more niche. There's a whole industry, cottage industry of tailored ligands, for example, Jinquan's beautiful monoprotected amino acid ligands that enhance particular elementary steps. But by and large, the community uses phosphine ligands and heterocyclic carbene ligands, as well as nitrogen-based ligands. These are the most commonly used. So let's talk about phosphines and NHCs because they illustrate most of the key points. They're stable, and they form stable bonding interactions with metals. Sometimes they can come on and off, particularly when you start to fit many phosphines around the metal, then each additional phosphine is destabilized through steric clashing. So we've got monodentate phosphines and we've got bidentate phosphines. And within the bidentate category, there is this descriptor that you will commonly hear called bite angle. And bite angle, I've tried to depict it here, refers to this angle that's formed between the two arms of the phosphine as they're coordinated to the metal. There's the coordinated form of bite angle, and then there's what's called the natural bite angle. And these are not equivalent. So this is important just to spend a minute unpacking. Coordinated bite angle is kind of less useful as a ligand parameter because what you normally observe empirically is governed by the metal valence. So if you look at a whole series of bisphosphines and you coordinate them to square planar palladium-2 D8 metal, it will hover very closely around 90 degrees. Why? Because the metal wants to be 90 degrees. So it's not that useful a parameter. Natural bite angle is more or less agnostic to the metal. It's a molecular mechanics calculation where the bisphosphine is tethered to a dummy atom, and then to just ask the question of naturally what angle does it like to adopt. And so then and I think a probably underutilized but interesting descriptor is the difference between the natural bite angle and the coordinated bite angle, because that really gives you a readout of how much strain accumulation you're getting upon coordinating to the metal. And then related to natural bite angle, there's a descriptor called flexibility range, which is also, I think, quite intuitive to understand. It just asks this question of what are all possible bite angles that are energetically accessible within 3 kcals per mole. So this is a flexibility versus rigidity descriptor. So let's just consider then a couple, just to keep our brain going. We've got a series here, DPPE, Xanthphos, BINAP. And first, like qualitatively, which do we think will have the widest bite angle? Which one do we think will have the narrowest bite angle? Soichiro, we haven't heard from you in a while. What do you think? Oh, sorry, I made you get up. That's why I don't like to, that's why I'm afraid to call on you, because you have extra work to do.
Sorry,
Answer.
you're getting,
We can hear you. Yeah. What do you like here? What's the narrowest bite angle?
in these examples,
Which one?
sorry, could you tell me again the question?
DPPE, Xanthos, BiNAP. Which one has the widest bite angle? Which one has the smallest bite angle?
I guess that force is widest.
Xanthos is widest. I think I've drawn it, I realize I've kind of drawn it suggestively here, so that's fine. So Xanthos is the widest, okay, and then between BiNAP and DPP, what do you think is next?
Binap is the smallest.
BiNAP is the smallest. Why do you think BiNAP's the smallest?
I guess the conjugated aromatic system make this.
Okay, yeah. Yeah, you've got two competing factors here. You've got the chelate, the size of the ring. So in DPP case, you've got metals 1, 2, 3, 4, 5. So this is a 5-membered chelate structure. In the BiNAP, you've got how many? 1, 2, 3, 4, 5, 6, 7.
Oh, I see.
You've got 5 versus 7, but you've got more atoms, more of the intervening atoms are sp2 hybridized in the BiNAP case. So those are the two competing factors that we care about. And you thought that sp2 won out, but do you want to reconsider?
Yes.
Okay.
It looks like to me the DPPE is a narrow binap.
Okay, and let's throw some numbers down. So 11. Super, that's it, Suichiro, thank you. So we've got 111 for Xanthos, 92 for BiNAP, 85 for DPPE. And well, I'll just linger on Xanthos, particularly because it has this interesting property that the bite angle is actually wide enough that it can adopt this additional coordination mode, which we call trans-spanning. So very wide bite angle ligands have this ability to, in a square planar metal, coordinate in a trans fashion. But Xanthos is kind of on the edge here, so it can actually coordinate both. DPPE and BiNAP are typically only 6. And thinking back to our, yeah, Rico.
I just wanted to ask, like, a follow-up question to this. What are the benefits of using a phosphine ligand that's small in the binding?
Oh, that's a good question. So let me comment on the next point I was going to make. So wide bite angle ligands can be useful in accelerating reductive elimination through this phenomenon of squeezing out. So to the extent that reductive elimination is one of only a relatively large number of elementary steps that we care about. If I told you wide bite angle was good for that step, then what step would narrow bite angle be good for? What's the microscopic reverse of reductive elimination? Oxidative addition. So that's the yin and the yang of ligand design. A ligand that accelerates one elementary step through being wide bite angle would likely suppress an equally important elementary step in oxidative addition. So that's the key. Phosphines have this interesting property that is distinct, at least compared to the nitrogen-based homologs. So, and this was elucidated first by Mislow of Mislow-Evans name reaction fame, Kurt Mislow in the 1970s. That is that chiral at P phosphines have a relatively high barrier to inversion. This is not true with amines, so you never see chiral at N ligands because the inversion barrier is too fast. But phosphines have this special property, and so and it turns out the inversion barrier is also insensitive to the identity of those groups. So this property elucidated by Mislow led to the development of the first generation of chiral at P phosphines. So let's think about the timing here. So Mislow made this observation in the 1970s. What we'll talk about in a moment is that Wilkinson's first discovery of triphenylphosphine as a ligand for homogeneous catalysis was in the 1960s. So people know that triphenylphosphine is a good ligand for homogeneous catalysis. Then the community learned that chiral at phosphine ligands are actually, their stereochemical identity is stable over time. So that naturally led the community to explore how switching to chiral at P phosphines might affect enantioselectivity. And then that eventually was integrated into a bidentate ligand design. The first that was a major success was DIPAMP, which won Knowles the Nobel Prize for his L-DOPA work. Just to review, you have this in your notes already, so don't feel free to just acknowledging that this is a repeat. So in terms of the bonding and electronics, we know phosphine ligands are strongly sigma donating. Depending on the substituents, they also have pi accepting character. The nature of that pi accepting character is through donation into a sigma star 3D orbital mixing model. And in the early days of use of phosphine ligands, it was thought that the open 3D orbital on phosphine was the predominant back bond contributor. And over time, people have realized that the anti-bonding phosphorus carbon bond is actually a major player. And this orbital mixing model is that most apt descriptor. Okay, that takes us to problem of the day number 3 from last time, and then we're caught up here. So this one, I'll switch over. We're thinking back now to the electronic effects of phosphine ligands and the molecular orbital description and this concept of using CO as a beacon for reporting on the electronic properties. So first question is, I think, a straightforward one, which is we've got, so we'll go to a nickel master, Amy. You've got nickel hexacarbonyl, and then we're going to replace one of the carbonyl ligands with a phosphine ligand. So what's going to happen to the CO stretching frequency of the remaining bound phosphines?
I would think that phosphine is a strong sigma donor ligand. So I think you'd have a more electron-rich metal center, which will lead to more back bonding, so it increase the CO bond stretching.
So you are making the stretching frequency. Did anybody get anything different? Oh.
I think I like Amy's reasoning, but I think the more electron-rich metal center would, like, if there's more back bonding, lower the bond order, I think that should lead to a lower CO stretching frequency, not higher.
I think it's just the last step if you're launching.
Yes, that's right. I'm like flipping.
Everything else.
Yes.
I always have to go through this whole exercise in my mind. It's like, is it more triple bond or double bond? Does the triple bond vibrate faster or slow? What is that, and then like, what's the IRE? So if that takes you a long time to think through, you're not alone. But I always actually just think it through every time. I don't try to have any special mnemonic device or anything like that. Okay, B. now we've got a series. We'll stay with you, Amy. Alkyl phosphine, aryl phosphine, phosphite. We'll just generalize it like that. And what do we think is going to happen across that series for CO stretching frequency?
Okay, wait, now I have to like make sure I'm getting my, I would think that the terbutyl group is gonna have be more electron donating, so that's gonna have a lower CO stretching frequency, right? Give it more electron rich center.
You tell me.
I think
You're on the clock.
I think that's right.
Okay.
Um,
And then what about phosphine
Yes.
versus phosphite?
phosphine is next and phosphite is the highest.
Why phosphite is the highest?
Even for electronics, that it's more electron withdrawing, so you're gonna have worse sigma donation.
More electron withdrawing, so you have worse sigma donation. Okay. And then what about the back bonding or lack of back bonding?
I guess. Sure, I guess you'd have, I guess you'd have more back bonding, the phosphite, it's more electron withdrawing, so.
They're better, yeah, better pi acceptors. So one way to explain that, not the only way, one way to explain that is to say PO bond has, remember that back bonding has this PC sigma star antibonding orbital component. So the PO sigma star antibonding orbital is lower lying than the PC antibonding orbital. So it's easier to donate into that lower lying orbital. And we can actually take that to the extreme. And if we consider trifluorophosphine, that's even more extreme, as a direct consequence of what we just discussed. And actually, trifluorophosphine is such a strong back bonder that it is actually becomes similar to the CO stretching frequency of the corresponding CO itself. Good. Any questions on that? Here.
I was wondering, we looked at this question through the lens of more or less purely electronic factors. How much of a factor does cone angle have? Because if you're distorting the geometry of the CO ligands, you're not going to have the same bonding interaction. So I would imagine that the
Good, yeah, good. It's a good question. All of these, so this analysis works as long as the series is isostructural. If you are, and Josh actually mentioned this, if you're comparing complexes of different point groups, different symmetries, different geometries, then it's more difficult to do a direct one-to-one CO stretching frequency comparison. And that's kind of what you're saying, is if you have something that's so bulky, it distorts the metal's geometry, then it's not a one-to-one comparison. And likewise, if you, in this case, what would happen if you have a ligand that is too bulky, you could, well, first you might not be able to get it on the metal as one extreme, but if it's so bulky that it wants to knock off other CO ligands or something like that, then that's going to create a complicating factor. Okay, Pierre had a nice transition there about steric descriptors. And the one that he introduced us to was cone angle. What is cone angle? It has this very quaint origin story that Chadwick Tolman, many years ago, prominent physical organic chemist, actually created these ball and stick 3D models out of wood and took a protractor and measured this angle, which he called cone angle. So this acknowledges that phosphines, if you think back, if you just visualize what they look like in three-dimensional space, they resemble, in the space fill model, they resemble cones. And so the cone angle is nothing more than the angle created by a phosphine upon metal binding between its outmost substituents. And it's really useful for being a first pass approximate of, bless you, approximation of steric bulk, but it does have its limitations. And so the limitations of cone angle have prompted the community to think about other descriptors. So those disadvantages are, one, we know that any organic molecule is dynamic and phosphine ligands are no exception. So each of the different, like let's imagine a simple case where one of the groups on a phosphine is an isobutyl group. And if the isobutyl group is facing this way or this way or this way, each of those have different cone angles. And so it does not capture conformational flexibility, and it does not capture that if you have three different phosphines, all with different substituents, so methyl, phenyl, T-butyl, then actually how you measure it would give you different values, which two groups you include in the measurement. So that led the community to come up with other descriptors, I said, and I'll introduce one that you will never hear about again in your chemistry education, just so I can introduce this to you and then describe to you what it is replaced with, because it captures the spirit of something important, but it was too complicated for the community to understand. So this is a concept called solid angle, and solid angle is predicated on the same concept as when you do shadow puppets with your hands. So we've all done this as kids. If you haven't, I'm sorry you missed out on that pivotal experience in your development, and that is that it considers the metal as the light source, and then defines a sphere around this hypothetical light source. And the area of the sphere that is in shadow as a function of the ligand is defined as A, the shadow area. And the solid angle then is, you can see the formula, it's A divided by the radius that you use to define the sphere of the light source. So why did this not catch on? It's because if you're confused, that's why it didn't catch on. It is not intuitive, and it's not easy to measure, although now with computational techniques, you could measure it. So it's not widely used. So what did the community turn to instead? One is a concept is buried volume, which is actually quite closely related to this. I'll introduce that in a minute. And the other are these other physical organic descriptors that these are useful outside of the realm of, and actually they were first developed outside of the realm of organometallic chemistry, inference values, A value chart, and Taft. So what we're doing now is we're superimposing that framework that already exists. So stereomol, for example, came out of the medchem literature, and then we superimpose that framework onto ligands and use it for descriptors. Stereomol is kind of complex. It's this suite of descriptors that account for the multi-dimensionality of many common organic groups. So if we consider the isopropyl group, for example, this is like probably one of the, even though it's kind of complicated to explain, it's one of the simplest illustrative cases. And Wenji actually wrote his Wikipedia article for the class on stereomol descriptors. So if you have questions, ask him, don't ask me. So isopropyl group, effectively, there's a constellation of descriptors that you can use. And so isopropyl group, just to introduce that, you have a B1 value that is shown here. That's the difference between the carbon and the smallest group, which in this case is the H that's directly bound to carbon. And then B5, which is the distance between carbon and the outermost reaches of the largest group. And then you have L, which reads out effectively the how far that largest group is Oh, sorry, L is the, yeah, is the readout of how far, if you imagine the bond to the isopropyl group is my pencil, L reads out like orthogonally how far that projects from space. Is that right? Or in that case, it's not that's how much it is in the same direction in space for L. Is that right, Wenji?
It's the length of the axis, so.
Length of the
it's
axis,
one-
yes.
A different definition than B1, B5, but if you read the article that I wrote, you can see the illustration there is probably gonna be more clear.
Okay. See Wikipedia.
Yeah, just type in sterol.
The details are not important. I don't think any time in your career, someone's gonna ask you, define the difference between a B1 and B5 stereomole descriptor. That will never happen. The key point is that through, multi-dimensional groups require multi-dimensional descriptors. And so you build a more complicated descriptor library to capture more structurally complex groups. Of course, I just have a small point here that ligands coming on and off is an important part in catalysis. That should not be a hot take at this. So let's talk about NHCs. We've introduced phosphines, and then their counterparts, of course, are NHCs and heterocyclic carbines. They're more strong sigma donors. They are weaker pi acceptors. There's, as I mentioned in the previous class, there's some debate about their level of pi accepting character. It's certainly small. Some people think it's 0. And phosphines, I think their coordination chemistry tends to be a little more dynamic, particularly with things like triaryl phosphines, whereas NHCs, when they're on the metal, most times they're on the metal for good, with some rare exceptions, like when the R groups contain very electron withdrawing groups that can force them to be coordinatively dynamic. And being here in San Diego, I can't help but introduce a related family of ligands to NHCs. These are the cousins that are called the CAC ligands, cyclic alkyl amino carbene. And what you've done here is that in the NHC, you've done a point mutation of one of the nitrogen groups to a quaternized carbon group. So what does that do? That raises, that the overall effect is that it makes these ligands more extremely amphiphilic. It raises the HOMO and it lowers the LUMO. So that's a similar concept to what we saw in Josh's lecture with the BF ligand, is more extremely amphiphilic than some of its isoelectronic counterparts, more strongly sigma donating and more strongly pi accepting. So the rise of NHC ligands is part of what accelerated the development of descriptors outside of cone angle. Why? Because whereas phosphines are generally shaped like cones, and there are exceptions to this, like the Buchwald biaryl dialkyl phosphines are not really cone shaped, but first pass, most of them are cone shaped. NHCs are not. NHCs are shaped like birds. And so cone angle is just a meaningless descriptor for NHCs, and that led to the rise of this descriptor buried volume, which was first coined or first defined by our chemist of the day. I don't know if anybody recognizes him from the day 9 worksheet. This is Steve Nolan, currently of Ghent, but previously at St. Andrew, is it St. Andrews, ICIQ, and started his career in the US at New Orleans. One of the pioneers of using NHCs as ligands for metals. You can compute buried volume using this online tool. We've done this in the group. I don't know, Wenji, have you done this using this tool? Okay. So one of the things that is cool, this is not totally in fashion yet, but I think will become more and more in fashion, is that this concept of buried volume can be useful. You can replace the metal with any main group element that you're interested in, and you could then use it as a readout steric descriptors more generally. So I've seen this applied, for example, to boron substituents, just asking the question of like, is this diol on this boronate ester more or less sterically encumbering? And you can use buried volume as a readout of that. It does have some drawbacks. So one is that it still does not fully capture conformational effects. And so depending on which way the substituents on the NHC or phosphine are oriented, buried volume can look bigger or smaller. And this has become appreciated in recent years by the catalysis community. There's this nice collaboration by Abby Doyle and Matt Sigmund, where they use a parameter that they call buried volume min. So it looks at the Boltzmann weighted distribution of conformations and their associated buried volumes, and then uses the minimum as a readout predictor for reactivity. Buried volume, this is not really a drawback. This is just you could convince yourself it's a bug or a feature, but depending on how wide you set the radius, it will give you different values. I don't think that's necessarily a bad thing, but it is just a feature slash bug. And then it still doesn't, it just treats each group as equivalent and does not consider its electrostatic potential. And so it doesn't give you a full sense of the electronic environment within the secondary coordination sphere of the metal. And so another tool, this is not so much a parameter, but it's a set of parameters, but as a tool are these steric topological maps. And in previous versions of the class, I just made this statement that this exists, and I didn't actually show what these look like. And then I realized that that's not actually helpful to anybody. So I tried to actually import some images here to show what these look like. I can't draw these, of course, myself. So here's an example from Ken Hauk and John Montgomery collaboration that was led by our collaborator Peng Liu from his time as I guess it must have been a PhD student, where they look at steric contour maps of 3 different NHC ligands that were found to be effective but give different selectivity in this Montgomery type reductive alkyne aldehyde coupling reaction. And so this is just give you a flavor for what these steric contour maps can do. The X in the contour map below is the alkyne substrate. And so you can see the alkyne substrate sees very different steric environments, even though, and this is the point, this is the only point I want to make and leave you with, is that even though the buried volume of the ligand on the right is smaller than the ligand on the middle, you see in practice, the steric bulk that the substrate actually sees is much greater. And so these maps can help tease out those subtleties that you lose in a simple buried volume calculation. Okay, so we're at time. I'll just give you a preview of some hydrog stuff. So it looks like probably for the midterm, we'll get through hydrogenation and maybe a teaser of carbonylation, but don't focus too much on your prep on carbonylation stuff, since we won't totally finish that. It doesn't seem like at this pace. So now we're off to the races. We're going to be focused on applying the concepts we've learned to catalytic reactions, starting with hydrogenation. And the first thing to think about that I'll leave you with is the problem of the day number 1 from the day 10 worksheet, which is Wilkinson's catalyst. Think about how you would make that if you were in the 1960s and that didn't exist on planet Earth, how you would go about making it. And then start thinking about how it reacts. We've talked about metals needing to get on cycle. How does it get on cycle? How does it form its reactive species? In what order of events? What are the order of events? The subtlety here is there's subtlety, but it's important subtlety. Does it initiate by reacting with H2? Does it initiate by reacting with olefin? These are all points that we'll cover next time. All right.